very nice and very extensive dinner. So I'm glad to see that you made it. I'm also glad that I made it after Fernando made me drink more caipirinhas that I would have ordered myself. So today will be another lecture on machine learning, but today I will actually address unsupervised learning and using clustering algorithms. And now also the type of data we're looking at is slightly different. It's again going to be topographical data, which I explained yesterday, but now it's going to be on surface damage created on tissues, again, from the biomedical area of my research. So, so yesterday we talked about slime. And today I want to talk about medical devices and how they interact with tissues in the human body and why friction there can sometimes damage the tissue, how we try to prevent that, and how we lay data on look at the damage that has been created, and that's where the machine learning will come into play. Yeah, I guess you never think about it because it's a system that just works very well for most of us. If you blink your eyes hundreds of times during the day, it's effortless. It's not a problem, unless maybe some dust or so gets into the interface between the cornea and the eyelid. And the reason why this works so nice is that you have a special liquid in between the tissue and the eyelid, and that's the tear film. And the tear film contains my most favorite molecule, the one I talked about yesterday during the colloquium, those mucin glycoproteins. They are really nice lubricants. It's not the only component. Obviously, the major component is water, but water is a terrible lubricant. It actually does not reduce friction at all. So here, the reason why tear films are a lubricant is because of the mucins in there. But it doesn't work well for everyone. Some people suffer from a condition that's called keratoconjunctivitis sicca, dry eye syndrome. And if you have that, then one thing is not going to work for you. You will not be able to wear contacts. So actually, when I look into the audience, I see lots of people wearing glasses. Fernando, Ralph, have you ever tried contacts? No? No? Anyone here in the room that tried contacts and then decided, no, it's not going to happen? Why not? So has anyone tried contact lenses and then decided you don't want to go along with it? Yes? Why? Yeah, it's very, exactly. It feels irritated, uncomfortable. You can even see that it starts to become red, which is a sign of inflammation. And probably you have a slight issue with the production of mucins in your tear film, and for most conditions it's fine. But if you try to insert an artificial object into that interface, then the lubrication gets disturbed, and then if you don't have the full spectrum of molecules you would need, then it's very uncomfortable. So then, yeah, that's why contact lenses is not for you, but you're not alone. 10% suffer from this condition where the tear film is not as good as it's supposed to be. Okay, so if you have that, then wearing contacts is not for you unless you do something. And the reason why the mucin provides such good lubricity in the tear film is twofold. This I want to briefly explain so you heard about it. So these molecules and other molecules we have in different locations in the human body can do the same, provides two mechanisms. The first one is called a sacrificial layer formation, and the second one is called hydration lubrication. Let me very quickly explain what I mean. Imagine that you're walking down the street, and just before you, someone dropped a banana peel. Obviously, if you step onto the banana peel, you're going to slip. Because it's getting removed from the surface once you apply the mechanical shear force, and you might land on your backside. What happens to the banana peel afterwards, once you stepped onto it, it will fly away a meter or two, and driven by gravity, it will be pulled back to the surface. So you can step onto it again if you don't pay attention. Obviously, for a molecule, gravity doesn't play any role because gravitational forces are way too small for molecules to actually do anything. Also, the interface of our cornea is vertical. So there's a different reason why these molecules bind to the cornea. It's a combination of electrostatics and hydrophobic forces that pull it onto the surface. So when you shear it off, it will find its way back, driven by this combination of physical forces. So which means you can always shear it off under a mechanical force. So when you blink, this happens. And this shearing off is kind of partially removing the friction between the interface. The second mechanism requires the first one to occur because once the mucin is bound to the surface, it can provide a surface-bound water film. And it's doing so by actually immobilizing lots of water molecules along the chain of the glycoprotein. There are all these glycans along the polypeptides, and all these glycans can very nicely bind water. So you create a surface-bound water film that makes the interface very slippery. And together, those two mechanisms are really, really great in reducing friction. So compared to water, when we measure friction in a technical setup, the friction coefficients we get with a mucin solution is a factor of 100 lower. So it's really, really, really efficient, and it's way more efficient than what oil-based lubricants can do. So when I talk to colleagues from mechanical engineering that study oil-based lubrication systems, they're always very jealous because nature is so much better in getting this job done. So that's what's supposed to happen, and if you don't have enough mucins in your tear film, you have a problem. So what can you do then? That's a big question, and that's something we have been working on. So we also developed a setup where we can measure friction directly on the eye. These are porcine eyes. No students were harmed in this study. So also these eyes we get from a butcher, basically. And then we developed a setup where we can actually fixate the eye on a sample holder. And then up here, this is part of a device that's called a rheometer. It's typically used to measure viscoelastic properties, but we kind of repurpose it in order by adding a cap of silicone and then attaching a contact lens to that cap. And now the contact lens can be brought into contact with the tissue, and it can be rotated on the tissue, thus creating a sliding force. We can also control the normal pressure so that we, to a level that makes sense for a physiological setting. And then we can get numbers and measure the friction at this interface between a tissue and an artificial medical device. And we can do that in the presence of different lubricants. And this might surprise you. If we, as a lubricant, use only a buffer, so just water with a small buffering molecule, no macromolecule at all, we basically find the same friction coefficient as for a mucin solution, which is supposed to approximate the tear film, and also for a solution of hyaluronic acid. Hyaluronic acid we use because if you go to a drugstore because you have dry eyes and you get teardrops, they will contain this macromolecule. And the reason that AHA is sold as a teardrop solution is the following. You also find it in a different interface that we'll talk about at the very end of my lecture today in knee joints. There, AHA is one of the key components to provide lubrication. It's much easier to purify. It's commercially available. If you want mucins in larger quantities, then you only get them in my lab, actually. So there are not that much available. That's why the commercial solution is to offer AHA. But now you can say it's fine, because friction is across the board is always the same. Why do I even need the mucin? Why did I tell you that, having not enough mucins in the tear film is an issue? And you said it's not great, right? So there must be something there. And the reason is that friction and surface damage are phenomena that do not need to be correlated. That might be very surprising to you. It was very surprising to me when I started working on tribology 11 years ago. You can have low friction and high damage, and you can have high friction and low damage. Let me very quickly give you two examples where you understand that this is true. If you rub steel across steel, and you have no lubricant whatsoever in between, it will give you a terrible sound. The friction will be extremely high, but probably the steel spheres look fine afterwards. However, if you rub steel across Teflon, which is rather soft material, then the friction coefficient is quite low. But afterwards you see there will be terrible scratch marks on the surface, which you might know from home if you fry something in your Teflon-coated frying pan and use a fork or a metal spoon in order to scratch around, then the surface gets damaged very easily. So you can have all combinations of high-low friction and high-low surface damage, which means we need to look at the tissue afterwards because we cannot predict if we find damage or not. And that's actually the dangerous part for our eye. If you have high friction, it just means you need more force to move your eyelid. Okay, but if you damage your cornea, that's a problem, right? Because then your eyesight will suffer. So we actually do not care about friction. We care about tissue damage in this situation. All right, with this setup and with this device I showed you yesterday, we can, after this experiment, inspect the surface of the tissue. This again makes use of this confocal laser scanning microscope where we scan the surface point by point and get a 3D image. This is just a 2D projection of the image in grayscales because you can more nicely see the different morphologies of damage that we find. So here what we did is actually conducting experiments on porcine tissues. Before doing the test, they looked fine. So here basically you don't see anything exciting. It's a smooth surface that you would expect to have. And then if we rub over the tissue with a contact lens without providing a nice lubricant or anything else, so that's the bad situation when you have dry eye, then afterwards it looks like this. And this was a 1-hour test. So you can imagine if your tear film wouldn't be there protecting you while you blink your eyes all day, that would be terrible. Then you have all kinds of damages on your tissue, and that's something for sure we want to avoid. So first take-home message, if you try contact lenses, if it doesn't feel good, stop using them, because that might develop. Yeah. Okay, but what you also see is that the surface damage we see here looks very, very different in every image. The morphologies can be very, very heterogeneous. Yeah. So, and that's something that we were also surprised by, and we're wondering what to do. But first, let me tell you that we found an issue for those people who until today cannot wear contact lenses. Yeah, first of all, we looked at the surface damage created by this rubbing process. And here you see a parameter that I showed you yesterday, the SQ parameter. That's the standard deviation of the Z profile of a surface. Yeah? So if this is low, the surface is smooth. If it's high, then you have a rough surface. Before treating the tissues, there's a certain value, and this value is heterogeneous because tissues from different animals obviously are not identical. So there's a certain variance between different samples. That's okay. But if you then rub over the tissue and use only buffer as a lubricant, you see there's a clear increase in the surface roughness. And this actually quantifies the impression you got from the images I showed you before. Things happen that should not happen, but they do, so the surface roughness is increased. However, if we use more fancy lubricants, either the hyaluronic acid-based solution or the mucin-based solution, then there's no difference compared to the initial surface roughness, meaning no surface damage is happening. And that's great news. So first of all, you can keep buying the HA drops from the pharmaceutical store. They work. They don't just sell something to you, but they actually work also in the lab. But you also see that if you have certain concentration of mucin that's high enough, not a low concentration, that's the dry eye part, then you're also fine, and that's what's happening physiologically. Okay, so far so good. Now, I promised there's a solution for people who suffer from dry eye, because we then said, if people do not have enough mucin in their tear film, of course you can try to use eye drops with mucins and then every hour or so add them to your cornea, but that's very inconvenient. How about we immobilize the mucin on the contact lens, and maybe then it does a similar trick as when we use a solution. So this is the same chemistry I showed you yesterday already, so this is a little bit of redundant, but redundancy sometimes is good. So also here the contact lens is treated with different steps. First with a plasma treatment to activate the surface, then we have the silane layer, and then this carbodiamide-based coupling chemistry, so that then the mucin is firmly attached, covalently attached to the surface of the contact lens. Amazingly, though, you don't see the coating at all. If I would have brought you contact lenses that are coated, they look completely transparent. If you do measurements on them, they're completely transparent in the visible light spectrum, so the optical properties do not suffer at all. Actually, we had a project here together with a contact lens company in Germany, the company that invented the hard contact lens in the first place. And they were also really amazed by the optical properties that are and how they are maintained by our coating. So that's really nice. But this is I don't want to talk about today. I just want to show you that an untreated tissue, if you just rub a contact lens across it, you get this increase in surface roughness, which is really not nice. However, if you have this mucin coating on the contact lens and do the same experiment, then it looks again identical as before the experiment. So no surface damage whatsoever, and that's exactly what we want. So there's hope for those of you who want to wear contact lenses, but at the moment cannot. So if this company at some point creates a product out of that, then you might be able to wear them as well. And here you can also quantify this impression with another parameter that we had already yesterday, SDR. That's the total roughness of a surface, right? The net surface divided by the projected substrate surface, and there you see with the coated lenses, there's no increase in surface roughness. So we are very sure that the system works really well. But from a topographical point of view, we have this issue. So when doing these experiments and you get eyes from the slaughterhouse, obviously the butcher is not always careful when removing the eyes. So some of them have some initial damage from the extraction process. And obviously there's also variance between the different tissues, and when you do this experiment, you now have to decide, do you work with this particular tissue or not? So in the past, we basically set up some criterion based on our experience, but it was somehow selected. It was not impartial. And it would be so much nicer if a machine learning algorithm could tell us whether this tissue is in good state or not, and whether a researcher doesn't have to make up some random criterion based on his or her daily mood. Right? So that would be nice. And also, as you saw the different morphologies in the pictures of damages I showed you earlier, they look very, very different. And some of them might have looked worse to you than others. But that's just our impression. Can we somehow, in an unbiased way, sort them into groups? like minor damage, major damage. That might also be nice for analytical purposes. Yeah? And I'm now motivating this on this condition, but obviously the same problem is very, very relevant in industry. When you manufacture whatever parts and you see some defect on the surface, you also have to decide, is this bad or is this something I can live with? And ideally, you would also understand where the damage comes from, but this I'm going to explain on Saturday, how we try to understand from a pattern of damages what was the reason that actually inflicted the damage. Yeah. But today we're going to stay on this particular problem. Okay, so here's a selection of damaged tissues, so images of those. And I think you appreciate what I said earlier. Now in the 3D representation, it can look quite different. Some of them look fine, some of them look okay-ish, some of them look not so nice. But if I would ask you to make groups of that, what would you do? Hard to say. Huh? How many groups would you actually make? Is it an okay group and a damaged group, or is there something in between? It's really difficult. Huh? And I guess everyone would do something slightly different. So we decided to ask a machine learning algorithm to do it for us. Now, in this particular case, we use unsupervised learning. So we are not telling the algorithm anything about the samples. We just, show them the pictures, or to be more precise, we calculate the same feature vector you saw yesterday, so a list of these parameters, give it to the algorithm, and then tell him, okay, do something, and tell me what makes sense once you see this data. And on this feature vector, of course, we first run netcore in order to reduce the dimensionality of the problem so that later on we get a better answer. This was something I was trying to explain yesterday, right? If you condense the feature vector, then finding a good solution is much more likely because you don't need that much data. Of course, we also rescaled the parameters. That's something that Ralph mentioned yesterday you should do to get a better result, because some of these parameters, just because of the way they're calculated, will have numbers in the range of a few thousands, whereas another parameter might give you numbers in the range of below 1. And we don't want to make sure there's bias, just because naturally some numbers live over here and some numbers live over there. So this is something that also happened. I'm not going to show it in detail. Yeah, and I said unsupervised machine learning is the tool that we're going to apply here, so there will be no labels attached to the feature vectors that we show to the algorithm. Okay, which algorithm did we select? Well, actually we selected a few, but this is the one I want to show in detail. It's called k-means clustering, and it makes use of a very, very similar strategy as the k-means classifier I showed yesterday. There, the idea was to actually use a metric, so actually to measure distance to neighbors and then decide, based on how the neighbors actually behaved, and assign a label of the query sample that you're trying to test. Now this is slightly different. Also here, distances between samples will be measured, and then depending on the number of clusters that you ask the algorithm to find, what's going to happen is that he will try to find centroids, so points in your data cloud, that later on actually will be the center of different groups, and in such a way that the variance within each cluster is minimized, while at the same time the variance between the clusters is maximized. So you try to find centroids of groups so that the distribution is more or less compact and you don't have lots of overlap between the different groups. That's basically what's happening. Okay, so let's do that. But now we have to first decide how many clusters I want. And one way of doing this, and that's what you find quite a lot in the literature, is to calculate a quantity that's called within cluster sum of squares. And then you can plot this as the number of clusters that the algorithm can find if you ask him to. And then you will see that if you change this number, there will be kind of this kink in the curve. This is called the elbow, where suddenly the slope of this curve changes a lot. And where you have these kind of slope changes, then it's suggested that those can be numbers for your clustering approach that makes sense. So the first strong change in the slope we have as a cluster number of 2. And then you can also imagine that at 4 clusters something is happening, but let's first see what's happening if we ask the algorithm to find 2 subgroups in our data. This is not the only way how you can decide how many clusters you want. There are also other quantities that can give you a similar result. For instance, the silhouette coefficient, the Harabash index, and the Bouldin index. I'm not going to explain what they do in detail, what the formulas are, but just so you understand roughly what's happening. Here, you want to have a high number, and if you find a high number, then this cluster number makes sense. And for this parameter, it's the opposite. Here, you want the number to be low. And now you can look at all these 4 quantities, and you can see again, if I compare all of them, what's the answer you will get? Yeah, 2 clusters seems to be, at least at first glance, the best option of how to subdivide your data. Okay, so we did not guess, but there are quantities you can use in order to get an inspired guess what cluster numbers might make sense. We will see that in a second. Okay, so let's ask the algorithm to do 2 clusters. This k-means cluster then will actually do that. And what you see on the left is a principal component analysis of the data. Now I need to ask, who does not know what a PCA does, principal component analysis, or can I just assume that you have all seen that? Or maybe the other way around, who knows what a principal component analysis is? That's not all hands? Okay, then I'm very, very quickly going to say what's happening here. So remember, in our feature vector, we have many parameters, roughly 20. After we run netcore, there are fewer, 9 or 10, depends on the threshold that you select. But in the end, the problem will live in a dimension that's at least 9-dimensional or 10-dimensional. And what a PCA does, and I hope Ralph corrects me if I say it wrongly, because I'm only an experimentalist. So it's actually introducing a coordinate transformation. It will show you the data points in a new coordinate system, and these are called the principal components, where each new coordinate is actually a combination of the parameters or the coordinates you had to begin with. So you always reduce it into 2, because then we can plot it nicely into D. There can be also more principal components, but more or less that's what it is. It's difficult to interpret what these mean, because there can be combinations of parameters that in the real world combining them doesn't make sense. Like, adding half of your age and twice your height, you can do mathematically, but what does it mean? And also for the roughness parameters, combining half the standard deviation and then a quarter of the peak values might also not be meaningful, but mathematically you can do it. And we only use it to get a first overview over whether or not this approach makes sense. All right. So this is what the data looks like, and now after running this clustering algorithm, he would actually sort the data like this, and all it's supposed to show you is it seems to be quite nice. So the data points seem to separate nicely after running this k-means clustering. Now let's see what happened to the actually data that we fed. And this is now shown on the right. So these are the parameters that were still left after running netcore. There are still a few, 12. And now what you will see in a second is that we get a subpopulation that is here marked in orange, another one in red. And if we now look at images that were sorted into these 2 different groups, this is a typical image sorted into the orange subgroup, and these are images sorted into the red subgroup. And if I would need to give names to those subgroups, I would call the first one smooth and the other one rough, so intact and damaged, which makes sense. I think it's the easiest answer you can get if you want to subdivide the pictures I showed you, those that look fine and those pictures which do not. It's maybe not the most meaningful answer from a material science point of view, because I also may want to understand if those are different from each other, but for a first shot, not bad. And you can see that most of the parameters over here actually quite nicely, they're quite useful in order to make this subdivision happening. We have the SQ and SDR value that in this case were both helpful. You can clearly see that the distributions of samples sorted into those clusters are quite different, but this is not the case for all of the parameters. So for these parameters boxed in blue, apparently that for this particular sorting problem, they were not helpful because the distributions I cannot tell apart. But there might be information still hidden in those if I increase the number of subgroups possible, right? Just for these easy questions I ask, they cannot help to address the problem. All right. So because this sorting result does make sense, but is maybe not the most meaningful there is, we went one step further and then said, what's happening if we cluster our data into 4 subgroups? Well, because that's the second point where the inclination of the elbow curve had a kink. And also in the PCA shown here, this again is only there to give us an idea whether this makes sense overall. It seems to be fine. Those clusters seem to be rather well separated, at least in this representation. And now let's look again at the data. So on the previous slide, those parameters down here were not useful for the 2-cluster problem, but if we introduce 4 classes, you can see now they start to contribute. Here, this parameter helps us to subdivide the yellow group from the other 3. Here, as the kurtosis actually helps us to differentiate yellow and turquoise from the other 2. So, as I said earlier, there was information. It was just not useful for the 2 clustering problem, but for the 4-group problem, it is useful. So that's kind of nice, and that's why it also makes sense to have, not completely eliminate all the features, because they might carry information that for some other problem is useful indeed. Now, this is then what the clustering result looks like. So here what we did is taking sample images from the central part of each cluster. So those are the representatives of what the ideal example of such a cluster group would be. And if you sort them, I think you agree this makes lots of sense. So what I see on the left side are samples that look really nice. I would call them pristine, almost untouched. The samples on the right side look terrible. If there's something like this on your cornea, everything is already too late. And in between, we have groups that are slightly altered. Here you can see that maybe the roughness is indeed slightly increased, but more or less homogeneously across the sample. That's what I would say. And here it's a more localized defect. It's not across the board, but if you have a defect, it's slightly stronger. So it is very meaningful. But again, let me ask you, would you have done the same 10 minutes ago when I showed you those images? Probably not. And I will convince you in a minute that actually, as humans, when we try to categorize some groups into samples or sort them into groups, we are not that good at that. So that's something that the algorithm actually does very, very well, because I fully agree with what I showed you on the last slide. I just wouldn't have done it myself. Yeah, and to convince you that it's not a random result we got with this particular approach, so I showed you data for the k-means clustering algorithm. There are also other algorithms out there that use a different approach in order to decide how to actually sort your data into groups. And especially with a spectral and the Gaussian clustering approach, we basically get something that's very, very similar. And we also ran some matrix to compare how similar these results are actually, so they kind of more or less fully agree on that. Agglomerative and Birch clustering, which I'm not going to explain how they work, they get slightly different results, but also not totally different. So overall, it seems to be quite reasonable and stable, the result we got. Yep. Oh, that's a detail I would need to look up. But I think for most of them, yes. I think for most of them, not for all of them probably. I think the Birch doesn't need it. Because its own agglomerative might not need it as well, because it starts from a large number and infuses them and so on. But yeah, I will have to look it up again to be sure. Yeah. Use what? No. No, that's what we ran. We ran those 5, and then we're quite happy that they kind of more or less agree. Of course, there are also more algorithms out there. And from a practical point of view, if you want to look at your data, of course, you always have to decide first what algorithm you use. Right? They might not give you the exact result. But what I will show you then also on Saturday, where I will mostly talk about knowledge transfer and few-shot learning with neural networks. This decision can have an impact, for sure. But at least from what we do and the problems we solve, a random forest is always a great start. It's very, very powerful, and it's also what other people have seen. And there are some other algorithms that are known to have issue with certain situations. So, yeah, if you want to get an overview, the first slide I showed yesterday had a reference to a review article I wrote with my previous PhD student. It's not for experts. If you know already machine learning, don't waste your time. But if you want to start with machine learning, that's also why we wrote it. It's giving an overview of what the different algorithms do, and it's kind of also giving you a suggestion what might be a good start for your problem when you try a k-means, when you try something else, and then typical examples that people have applied it for. Okay, yeah, so it looks quite nice. And now I want to convince you that the algorithm is actually better than what we can do. So we reduced the number of pictures. The total number of pictures we showed to the algorithm were more than 1,000, I think 1,500. And again, it's only possible because we have this nice microscope where you can very quickly get these images, otherwise you would suffer in getting all the data. But here we reduced it to a subset of 400 images because we also wanted to show the same images to my PhD students. Not Caroline, who did the study, but the others. And then we told them, please sort them into 4 groups. So we gave them the same boundary condition as for the algorithm, but nothing more. No further guidance, just the images, and then, everyone was asked to do whatever they wanted to do. But before I show you what they decided on, let's again see what the algorithm does with this subgroup of images. And here we have then in the end 4 clusters again, because we asked him to do 4 clusters. And even though we didn't give the algorithm any labels, we knew how the images were created. Those labels we kept hidden, but we knew the labels, so we can afterwards check what this clustering means. So there's data that we obtained with an uncoated contact lens that, as I showed you, creates quite some damage, and with a mucin-coated contact lens that, as I claimed, should not create surface damage. So let's see now what happens. If we now look at the red bars, This is now images from obtained with the coded lengths, and the algorithm sorts them all into cluster 1 or 2. There's not a single picture that would be sorted into cluster 3 and 4, which makes lots of sense. I claim that we don't see damage, and those two groups were the ones that look really nice. Obviously, there might be some pre-existing condition on the tissue, so there might be some stuff already there that doesn't come from the experiment. That's why it's also fine for me that we have some samples in this group. But there's nothing in group 3 and 4 which fully makes sense. On the other way around, if you look at the open bars, this was data created with an uncoded length, where we always see damage. There's not a single image sorted into group 1, because there's always damage. So I think this is a pretty nice and powerful result. It makes lots of sense. Yeah, yeah. And actually, yeah, from the other samples we see a whole bunch, but no cluster 1 example. So it's actually quite meaningful what you get over here. And now here's the data I mentioned. So we gave the same pictures to my PhD student and asked him to sort them as well. And now we can compare the sorting results of my PhD students to the sorting result of the algorithm. Obviously, you can also ask the algorithm several times to do the sorting and see if the outcome is similar. Ideally, this would be the case. And what we show here, it's a parameter, the adjusted mutual information score, that will tell you how similar the sorting outcomes are. If it's 1, then basically you get exactly the same result as in the previous sorting attempt. So here, if we run the algorithm several times, you see it's almost 1, which means he's quite sure about what to do. It would always create a similar sample, same sample into a similar group. That's nice. So it's not guessing, it's really consistently doing what it is. However, if you compare the results obtained by the algorithm to the results of my students, you see it's really not the same. It quite diverges. And even worse, if you compare the results that my different PhD students obtained, so Manuel to his twin brother, no, you did not participate there, but your twin brother to, let's say, Ufuk or Bernardo or whatever, they also don't agree. Everyone does something different. So there's a very, very strong dissimilarity between the sorting results. Even worse, when preparing the data set, Caroline made a small mistake, which in the end we were happy about. One picture she had twice in the data set. Just by reducing the number of pictures, she forgot, somehow made this mistake. So we could check if at least this picture that's twice is sorted consistently into the same subgroup by the panel. It's not. And that's what I meant earlier. I mean, if we are asked to just, sort something, everyone makes up a slightly different rule and slightly different categories that are important for you. But if we can't even stick to our rules ourselves, then that's tough. The algorithm is very consistently doing something that makes lots of sense. So we're quite happy with that outcome. Yes? Do you remember? But I think at the beginning they saw an overview, so they get a rough impression, and then one by one. Yeah. And then pictures, and you have to push a button, basically, 1 to 4 here. Yeah. Yeah. But the overview was not always shown. It was shown at the beginning, just to get an impression, and then. Okay, so what you learn, students are not very consistent in making decisions. That's something I knew before we did the experiment. No, Ralf is laughing. And the clustering algorithm is quite powerful and very consistent in what he does. So that's nice. Okay. So this was an example on unsupervised learning. What I'm going to do now, I'm going to introduce now the next experimental problem. And then I'm not sure if I will start with the machine analysis or do everything on Saturday. So Saturday will be quite heavy on machine learning, no experimental background whatsoever. It's going to be data and different ways to treat them, also CNNs and so on. But I think until then, there have been enough examples also of confusion matrices. You've seen now different algorithms, the KNN, the random forests. So I hope you will be able to follow. Yeah, and then in the end, Manuel will briefly show what he's working on right now in his PhD, because we are still struggling with the issue of not having lots of data for some situations and how to actually still make it work. That's basically the content of the last topic. But before we get there, I want to introduce the problem, why we do it, categorizing rare patterns. I mentioned earlier that this whole business of looking at damage can be very valuable for industry. If you see some damage on a product, it would be nice to understand where in the production line something went wrong. And for this, understanding what kind of process actually induced the damage would be helpful, so you know where to look. And surface damage can look quite different. That's what you saw. but maybe we can understand, based on the morphology, what type of process induced the damage. From a medical point of view, that's also relevant for cartilage, and that's why we're going to quickly talk about cartilage, and I want to motivate the medical problem behind it. Cartilage is a high-performance tissue that allows me to stand for an hour without feeling pain, or walking for hours without feeling pain. And while you're still young, everything is fine, but as you keep aging, the risk of contracting a cartilage damage increases, and this damage will not go away. That's why understanding also where damage comes from, especially when once you get an implant and the implant is not interacting well with the cartilage and it needs to be removed again in revision surgery, it would be great to understand why the system failed, and such a damage analysis then can help you understand why actually the implant didn't live as long as you want. So that's a more medical motivation, but the technical one I mentioned earlier accounts as well. So, cartilage. Cartilage we have in many different locations. There are two types of cartilage. One is elastic cartilage. That's what you have in your ears and your nose. And then you have articular cartilage. That's what you have in your knees. And articular cartilage is the one that's way more difficult to understand how it works, and also very, very difficult to engineer artificially. So there is no good cartilage replacement material to date. There's just not. So that's what it looks like. If you now dissect a small cylinder from a joint, then you see the bone tissue and the cartilage layer on top. And as I said, this we have in your fingers, in your knee, also in your hip, and that's what will create you problems when you're old. Elastic cartilage is not a problem. Articular cartilage is. Yes, I brought a fun video that will quickly summarize what the problem is, and then we look at damage.
Cartilage is this fantastic tissue that makes up that flexible part of your ear, the end of your nose, and the cushioning between your joints. It's also what the skeleton of animals like sharks and rays are made up of. If you're an athlete, understanding the basics of cartilage will help you prolong your career. Here's what you need to know. First, cartilage is a connective tissue like muscles and bones, yet they're also very different. If you break a bone or tear a muscle, you know it right away, because it's full of nerves. Cartilage, though, doesn't have nerves, so you won't know you damaged your cartilage unless it affects the underlying bone. Also, those bones and muscles will heal. Cartilage, not so well. But to get why, we first need to distinguish between a few different types of cartilage. There's elastic cartilage, which is very flexible and found in places like your ear. Then there's hyaline cartilage that is super smooth and tough. It has minimal flexibility, but its glassy smooth surfaces keep our joints sliding smoothly. Then there's fibrocartilage. This cartilage is tough and flexible, but not particularly smooth. It's found in places like your menisci and the intervertebral discs. Many people have this idea that cartilage doesn't ever heal or grow back. In truth, it can, but very, very slowly. Like other tissues, cartilage is made up of cells. These are known as chondrocytes. Now, when other tissues get damaged, they are able to essentially migrate to the wound and divide and multiply rapidly. Chondrocytes can't do that easily for two reasons. First, they're found in a thick matrix, so it's hard for them to migrate to new areas. Secondly, there are no arteries or veins in the cartilage, meaning there's no blood supply to help feed and nourish the multiplying cells. The limited supply they get through diffusion just isn't enough for the rapid growth that is needed. Let's take this example. So say you suffered a joint injury, like ruptured ligaments, menisci, etc. This destabilizes the joint, which in turn affects the cartilage in the long term by wear and tear. This process can take a year or a decade after injury, but it's not reversible. The early changes in cartilage are hard to feel since there are no nerves. But after losing most of the cartilage, the two highly innervated bones are exposed and begin to rub against each other. Yeah, and that really hurts. At this point, the doctor can only medicate the pain since most of the cartilage is gone. If detected early, sometimes doctors will try to encourage cartilage to grow back in the area by putting a bunch of holes in the underlying bone that penetrate the bone marrow. And they call this microfracture. This essentially provides a blood supply and allows some stem cells in the bone marrow to migrate to the injured area to regrow some cartilage. The problem is that it's not that nice, smooth hyaline cartilage that we want. It's essentially scar tissue like fibrocartilage. It does help protect the bone, but it's not as smooth as we'd all like, and thus doesn't work as well. Since the goal is that nice smooth cartilage, doctors have a few other advanced cartilage repair techniques. Often they'll take grafts from elsewhere, either your own cartilage or from a cadaver. But you can't just take the cartilage. You take a plug that consists of the cartilage and the bone. The implanted bone will heal quickly with your bone and hopefully lead to a successful operation. The problem with this is that your body may reject the tissue coming from another patient, or if you take the cartilage from another part of your joint, then you leave a new hole in your joint. For future repairs, scientists are working on growing these plugs from our own cells. For instance, one technique could be to take adult stem cells from your own fat cells that can turn into bone and cartilage. Then, through different techniques, tell those cells to either turn into bone or cartilage, and then insert that whole thing back into the damaged area. So, if you're an active individual, here's the key. Be kind to your joints and cartilage. You only have so much, and while it does have some healing potential, it's not much. Also, if you injure your joint, go to a trained orthopedic doctor right away. It'll be a lot easier to salvage your cartilage if you detect the damage early than if you wait until it's mostly gone. Cartilage is this...
Yeah, absolutely. So that's the second take-home message. Be kind to your cartilage. And I mean it. So in the last 14 years, I had 2 PhD students already who had that strong cartilage damage induced by sports that they cannot do any sports anymore but swimming. One was playing ultimate frisbee, you know, when you kind of toss the frisbee and then run across the field. And the second one was playing hockey. And then at the age of 26, you're done with sports, all type of sports. So try not to be too brutal. Because that's then what it can look like. This is an example of osteoarthritis. That's typically something that's not sports-induced, but comes with age. And osteoarthritis is an issue that's actually not that rare. In the US, it's quite common, actually. 20% of people over 45 suffer from it, and half of the people over 65. So the chances of you, at some point, encountering an issue with your cartilage are pretty high, actually. So try to postpone it as much as you can, because you saw in the video the options you have are not that great. Getting a cartilage transplant from a corpse is maybe not ideal, and then, you know, and also in these artificial developments, so artificial cartilage materials developed to date, they suck. They're not good. So we don't have a real solution. We understand the problem, but we're still working on a material science aspect to make a material that can actually be implanted to replace the cartilage. Yeah, obviously, there are risk factors here that will increase your likelihood of getting such a damage. So with age, it can come. Obesity, so overweight is an issue. Overuse of the joint, so some types of sports, as I mentioned, are really not good for your cartilage, and so on and so forth. And yeah, ideally, you try to avoid it. Once you have an issue, then one of the treatments that's used quite often is viscosupplementation. So here, then, you get an injection into the synovial cleft. And HA at the moment is the material of choice. So it's supposed to improve the lubrication in the joint. But it's not really working, at least not in the long run. So my secretary's husband got this 2 years ago. It was fine for a while, as for most people, but then after half a year or so, it's not enough, and then you need to move on to a next level of treatment, which mostly then is surgery. So it will delay your need for surgery, but it will not abolish it. Because you address the lubrication, but we have already a damaged area, right? And that damage will propagate, will become worse when you keep rubbing across it, and that's very difficult to stop. But okay, I mentioned this because it will motivate one type of surface damage that we see on cartilage, because you can test in the lab whether HA is good at preventing surface damage. Similar to what I showed you for cornea, we also do this test with cartilage samples. So this is untreated cartilage, which looks very nice. The surface is as smooth as it should be. And if you rub over it with a solution that contains only HA, well, we see some surface defects. So HA is okay in reducing friction, but not so great in preventing surface damage. Now you can say, of course, in the joint I have a biological fluid that contains more than just HA. That's true. It contains another molecule that's called lubricin. It's basically the small brother of mucin, very similar architecture, just smaller in size. And together they're rather powerful. But once you get a surgery in your knee, you also lose your synovial fluid, and you replace it with HA only, and that's not doing the job, at least not as good as we need it. Now you can say, okay, how about lubricin itself? Well, this you could in principle also inject if it would be available. But I only know one colleague worldwide in the United States who can purify lubricin. So it's just not there. And also, if you inject lubricin solutions, they alone are also not so powerful. It's really the combination that helps. So we run this test in the labs. Also here we see some type of surface damage, but a different pattern than here. Nevertheless, those two surface morphologies belong to the category of abrasive wear, because it comes from really the fact that you rub something hard across a material and you change the surface morphology. So keep this name in mind, because I will show you 2 other types of wear that later on are relevant. But this can occur if the lubricant is not perfect, and especially after surgery, it might be a consideration. Yeah, if this does not work, this supplementation of the liquid, at some point people get a hip implant. That's obviously something you try to avoid. And those hip implants are either made from metals, ceramics, or these days synthetic polymers, high molecular weight polymers. But also then if you keep rubbing with this implant material over other materials, even across cartilage, they will suffer over time and they will get damaged and will experience wear. And this has been tested in a lab. So here it's one of the materials that's used a lot, so ultra high molecular weight PE. And this rubbing test included several million cycles, so it was a long-term test in the lab for sure. And here you can see they measured the weight change of this particular implant over time, and the weight data points, the open symbols show you how much material got lost. It's significant. Where it's it's on, and the material you actually remove from the implant is typically small particles, debris particles, and those particles in turn can induce further damage either to the implant or to the cartilage. So such damage created by impacting particles is called erosive wear, and this is also a consideration in this particular setup, because once you have initial debris from your implant, it will make a bad situation worse, and then it will damage cartilage further. Okay, so this erosive damage is also relevant. We'll look at that later. Yeah, and then another option that I mentioned earlier, if you do not replace the joint with something fully artificial, you might be able to basically fill the gap in the damaged cartilage layer with a material that's somehow similar. I'm saying somehow similar because to date, there's no formulation that really approximates both the mechanical properties and also the friction-reducing properties of your tissue. This I cannot explain in detail, would take me half an hour at least, but the attempts made so far are okay, but not really great. And here's the, to date, best performing example that got published in 2016. They have been used this in clinical trials. It's the best that we have, but it has issues. It's a material based on a synthetic polymer, PVA, polyvinyl acetate, and it's a cross-linked polymer system, a hydrogel basically, and it provides high water content and it can reduce friction. But keep in mind, friction is not the only concern. If friction in my joint is high, I need more force to move. But in the end, I'm worried about damage. If I incur damage, I need to, again, replace the material, and revision surgery is very painful and costs money and so on and so forth. So the mechanics are okay, the friction is also fine. However, they then did rubbing tests with this material in contact with cartilage, and they saw two types of wear. The first one is maybe not that easy to see, but here on the left, because it's not a topographical image, then the image quality is not that great, but you can definitely see roughness structures on the artificial material that were not there when they made the material. So you have surface alterations that make the material more rough, and it's easy to imagine that a rougher surface will then create more problems in terms of damage later on. Even worse, if we inspect the other side of the friction pair, so we had cartilage on the artificial material, right? Then the cartilage, you will find damage on the cartilage. And actually what happens is that the surface of this material seems to be somewhat sticky, and in some locations it's ripping out cartilage pieces from the tissue. So it transfers material from the tissue to the implanted artificial material. That's of course also bad. Huh? This is called adhesive wear because, yeah, you were too sticky and you actually transfer material from one side to the other. So we have abrasive wear, erosive wear, and adhesive wear, and all three things can in principle happen on cartilage, and none of this is good. Yeah, because of that, because all these three types of damage that again are summarized over here, abrasive, erosive, and adhesive wear, with different reasons as to why they occur, we were wondering if we can recognize those three different types of damage based on the patterns they create. Yeah, obviously we would be interested in learning about this problem on cartilage. But remember, you need lots of images, and then treating cartilage and damaging it is actually not that simple in the lab, but also you need to somehow get this tissue and prepare the samples. It's very time consuming, so it was clear to begin with that we cannot create 1,500 images of damaged cartilage. We just cannot. And if you think about the problem, I'm motivated if after during revision surgery you try to understand where the problem was, you don't have 1,000 samples from patients suffering from this issue. You don't get it, right? So somehow we have to find a way to analyze a problem on this biological tissue without having all the data for the biological tissue. And that's what I'm trying to show next. How can you solve a problem for a system where you only have very little data by taking information from another system where you can easily get data? Obviously, the system cannot be super random, otherwise the morphologies would not be comparable, but let's see whether this works. Okay, then I will start with this a bit. And that was the plan, and that was the first project of Manuel's PhD. So we try to learn something about cartilage, but we have trouble getting information on cartilage. So we don't have cartilage, then we look for a material that is easy to get, cheap, and easy to damage. And Teflon does the trick. If you ever had a Teflon cube in your hand, this white material, you know it's quite soft. Scratching across it with your nail will be enough to induce damage. So it's quite easy to produce damage patterns. So then Manuel and me thought about how to actually create the 3 types of damage that we expect on cartilage to be relevant. So abrasive damage, erosive, and adhesive. So for abrasive damage, he just used sandpaper and actually slid it across Teflon. So something similar than a rough surface in the body sliding across the tissue. For the erosive damage that is created by impacting particles, he used a particle gun and then small artificial particles that he actually, with an airstream, shot onto the material, and that created impact damage, so erosive damage. And then for the adhesive damage, where we have material transfer, he actually glued 2 samples together, and then the glue will distribute on the 2 sides somehow. So that is kind of mimicking this material transfer side. Sometimes the Teflon surface got damaged also by this ripping apart process, but for sure we can mimic this material deposition on either surface. And here you see now images of what these different morphologies, how they look like. I think you get an impression that they're not the same. And if you would need to describe them somehow with words, I think that can be done. But obviously we don't want to describe them with words, we want to describe them with numbers. So actually this type of damaging works rather fast. So Manuel collected 700 images per damage type because Teflon is easy to process, and then the imaging is also quite fast. And then obviously we get the same type of data that I talked about already, lots of metrological parameters. And now if you look at that and you try to see if there is 1 or 2 parameters that allows you very easily to separate the 3 types of surface damage, it's tough. It looks more or less the same. Even though on the images we saw it's not the same. Yeah? But maybe machine learning helps us again, and that's what we're trying to figure out now. Okay, let's obviously reduce the parameters that we have. So we run netcore in order to condense the feature space. Also here it works. And maybe I just make this point again. Once we have a reduced feature vector and then calculate the variance inflation factor among those, remember this number should be low, because then we know that there is not redundant information among these parameters. It should be below a certain threshold, which after netcore it is. Before you can see there were clearly bars way above that. So again, netcore did what it's supposed to do. It got rid of redundant information. Those parameters were kicked out. And yeah, also it's maybe important to stress that you can never predict which parameter is important. In the examples that I showed you so far, SDR was very useful. Now netcore kicked it out. So it's not like you can make up a rule, always use SDR or always use SQ. It really depends on the problem at hand. And in this particular case, apparently, when you do the network and the correlation analysis, SDR was not super useful and could be replaced by another parameter carrying similar information. So this is quite surprising, but it's the way it is. And that's why I think netcore is useful, because it's doing this analysis in a very impartial way. Otherwise, I would always keep SDR. Okay. But in this case, it's not useful, so let's kick it out. And now then Manuel ran 4 different classical machine learning algorithms on this data. And 2 of those I mentioned already, and it's sufficient if you talk about them. So we have, again, the KNN classifier and the random forest. What these others do, I'm not going to explain right now, because the result is very similar anyways. So what you can see that we can very nicely get a high accuracy result of our groups. So now again, it's a label data set. Well, we know what a damage pattern, what group it belongs to. And also we use, again, now supervised learning here. That's what you need for KNN and random forest. And you see the accuracy is quite high, and actually the high number of images that he collected would not have been necessary. Okay, that's good to know. It's not like he spent months in the lab. I think it was a few days. But the high number is not necessary for this problem. But this is only Teflon. I want to learn something on cartilage. We are not there yet. Okay, so that's, yeah, accuracy is very high, and we can look at the confusion matrix to look at this a bit more in detail. The random forest classifier I like the best, because it also gives us the best results, and I can do something I will show you in a second. I can ask the algorithm why he made a decision. And this will come back in a second. So if you look at now the diagonal of this confusion matrix, then the numbers are really nicely and high. And there are some mistakes, but overall it's not that bad. So the overall accuracy is 93%. And if you look at the subcategories of quantities that tell you how well it worked, also precision and recall are very nice. So it seems to work pretty well on Teflon. That's already not bad. So it's possible to distinguish those, and this is what I meant just a second ago. Because we use a random forest, we can now ask every tree which was the parameter that was the most important for you to classify those 3 types of damages. And I ask a whole population of trees, and then you see the distribution of answers we get. And now these are 3 parameters that I have not mentioned at all so far in the examples I discussed. Again, as DR is not among them, this was kicked out by the algorithm, but now we have STR. STR is very different. STR describes the isotropy of a surface. It's actually calculated from an autocorrelation function that you look at a sample in different directions, and you calculate this autocorrelation function. And if there's a direction where something is popping up, you know that there is something going on the surface. Typically, line defects are detected by STR very well. And the abrasive damage that we create, there you have line features, so it makes lots of sense that the algorithm in the end uses, and random forest uses STR. So that's why I like it, because in the end I can partially check what the algorithm did and whether I understand the decision-making process. Here I do understand that. The second parameter that we found is the correlation length. So if you calculate the correlation function in one direction, we already had example in one of the previous talks, once you move 2 objects apart and suddenly the overlap will go down. So this will tell you if there's a sudden change in the height profile in our case. And when do we have a sudden change in this height profile? If you have material transfer from one side to the other, then at some point you get this edge. It's more or less like a step function where the added material is there and then it's not. So I also understand why the correlation length is useful for the random forest here. The third parameter I do not understand, but that's okay. I understand 2 out of 3. That's not so bad. It's a very exotic one. It's a complex parameter that quantifies the areal fraction that corresponds to the roughness peaks of a surface. So it gives you a percentage of the surface where you find roughness peaks. Yeah, okay, that can be relevant. Why not? Yeah? But it's not something I would have ever picked if you asked me to select an important parameter. Okay, so it kind of works, but now is the first nice and fun part I want to show you today. And I think after that, then I will stop. Because we understand the problem on Teflon. Maybe you can also understand the problem on a different material that's easy to treat, aluminum. Aluminum can also be damaged rather well with the methods I showed you. It's possible. It's not too hard, literally. And now the idea is the following. If we can either train our random forest, because that's the algorithm we want to keep using, only on data obtained on Teflon, and then try to show it samples, data collected on aluminum and see how it does. Or we do the following. So this would be a pure forest made up of what I would now like to call Teflon trees, because all those trees have been trained on Teflon only. Or you do something that's a bit smarter. You introduce a small number of different trees that actually have been trained on aluminum samples. Those, let's call them aluminum trees. So now I get a mixed forest, as you find them in Europe. And depending on how many of these Teflon trees you add to the system trained on, how many aluminum trees you add to the system trained on Teflon, we might get a better answer than just training our system on Teflon only. And now the question is, how much data do I need in order to train my aluminum trees in order to get a nice result? But that's the overall idea. Are you following? So most of the data is used to train trees only on Teflon. That's where the big number of data comes into play. And let's see if we can use a little bit of data to train a few trees on aluminum, and that's what we then call the hybrid problem. Okay, first of all, we want to make sure that this additional information that we're offering is used by this new mixed system of aluminum and Teflon trees. Because if I add data and it's not used by the new model, then it doesn't work. And for this, again, the Gini importance can be very helpful. So what I show here are the parameters that actually are used by the random forest. And for each parameter, you see a group of bars. And the lowest bar actually shows you what the pure PTFE model does. So it will actually give you the importance of this particular parameter when a pure PTF model does the categorization. But then as we keep adding aluminum trees, creating a forest that's more complex, that now also uses information obtained on aluminum, then you see the ranking of these parameters changes. So that tells us that indeed the decision-making process of the mixed forest is different as we keep feeding information obtained on aluminum. And this convinces us that indeed changing the forest by adding more and more information from the other material does influence the decision-making process. So that's nice. And this happens for almost all the parameters. Sometimes the ranking goes up, sometimes it goes down, but that's not really important how it changes. It just convinces us that indeed the system uses the data that we in addition feed to the Teflon data. Okay? Still with me? Alrighty. Now, how about the accuracy? So we can now show the aluminum data to a forest that's only trained on Teflon. And of course, it would be super if that would give us a good result. But I guess we all agreed that it's not going to happen. That would be magic. Yeah? Similar to this problem I showed yesterday, training the system only on slime and asking it to classify plants is not working. So that's why for the pure PTFE model, the accuracy is not good, a bit above 50%. Obviously, if you train a forest perfectly on aluminum, if you show it lots of data collected on aluminum and then ask it to classify aluminum samples, that works well. But that's not a surprise. So that's the line you see up here. It becomes interesting when we now try to mix trees that have seen during training Teflon with trees that have seen aluminum during training. Because then, starting with a pure Teflon trained system, the accuracy goes up very, very quickly. And here's a mixture of 100 Teflon trees and 50 aluminum trees. And this already gets a very nice result and is very close to a perfect system trained for aluminum. Okay, so in this system, we mix different numbers of trees. But now you can still ask how many samples, how many images do I need to show to those trees during training? Because that's in the end what I, as an experimentalist, want to minimize. I don't want to collect hundreds of images on a material that I don't have a lot of, right? And this is what the second graph is showing you. Now, for this geometry, where we have 100 Teflon trained trees and 50 aluminum trained trees, Manuel reduced the number of images shown to the aluminum trees. And once you reduce the training data, you can do it quite a bit, actually, without losing too much of accuracy. Going down to, what's this, 10 images still gives us a 90% accuracy in the classification result. 10 images on a material that's difficult to get, that's not so bad. So actually, we can do the most part of the training on a sample type that's easy to get and feed in a little bit of information obtained on the difficult sample by creating a mixed forest that actually uses the specific information to better distinguish what's going on, if the two problems are not too difficult. Going back to what I showed you yesterday, I mentioned already the reason why our approach failed, because we did it before we did that study. Those surface topographies on the plants and on the biofilms are too different from each other. Within the groups, sure, finding differences works, but if you cross-compare them, yeah, it's just too different. And here it's a similar problem. On Teflon, you get the three different morphologies. On aluminum, you get them as well, but they do look slightly different. And what I will do next, not today, but then on Saturday, I will show you how we take this one step further to move to cartilage, the real problem. So then we use the same idea. We try to use knowledge obtained on Teflon and aluminum in order to later on classify pictures obtained on cartilage. And I'll try to show you that also this works very nicely with a low number of images, and that's exactly what we want. Those clinical data after revision surgery, this will be sparse. 5, 10 images maybe, not 500. And I can tell you it does work. Okay, I think that's probably a good point to make a cut. And we restart this again. And then what I will also talk about on Saturday is a problem that from a material science point of view is more realistic than this, because right now we only look at single damage types, either purely abrasive damage, purely erosive, or purely adhesive. In a real setting, be it clinical or industrial, it's very likely you have combined damages, because impacting particles change the surface, and then if a rougher surface, this can create abrasive damage later on. So you might see a combination of damage patterns. And ideally, we would like to understand from the image what's going on. Is it erosive and adhesive, or adhesive and abrasive, and so on and so forth. And that's the ultimate goal, and we're almost there. So I can show you it's working. how to do it with few data that's somehow working, but manual is not done. Yeah? So this is what's going to happen in 2 days from now. Okay, and with that, I think I want to stop today and pick it up again on Saturday. Ah, lots of aluminum and a few Teflon? I don't think so. Did you? Okay, then the answer is no. Yeah, I think basically, no, you did lots of images on aluminum as well, right? You have, in principle, enough to do it. Yeah. So you could. You could. Yeah, you think so? You mean here? Ah, you mean the gene importance? Yeah, 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 true, yeah. Ah. Oh, you mean eliminate everything that's not here? No, because to be honest, I just here for random reasons highlight the first 3, right? I mean, you could also say only use the first 2, but I doubt that 2 are enough to, I don't know. Did you try and not tell me because I'm not aware that you did it? Okay, no, he has not tried it. But I doubt it works. Because, yeah, I mean, again, the STR make lots of sense, lines you will find, but the other 2 motives are more difficult to describe. So my gut feeling tells me that it will not work, but I might be wrong. Yes, exactly, and then you lose information, yeah. But it's completely possible that maybe the last 3 are not needed, yeah, but again, work in progress. Yeah? This just came out this year, this paper. Yes, come over so I hear you. Ah, you mean when we change the mixture ratio of the different trees? Ah, there you don't get this number. The support vector machine will not tell you this parameter. It's a particular property of the random forest that you can read out the decision criteria. So the gene importance you only get from the random forest. The KN doesn't do it because it only measures distances to neighbors and then does a popular vote type of thing. And the support vector machine will not give you that either. That's why I am so much in love with the random forest, because I have the option to afterwards, post hoc, ask the algorithm, why did you do what you did? So it allows me to gain a little bit of insight into the material science problem. If you only want to get a classification result, the other algorithms are also fine. But I always also try to understand what's going on and why. And that's why the random forest I like the best, because it's an example of explainable AI, more or less. So you can actually look into the decision process after it has been made. So you only get it from the random forest. From the support vector machine? Okay. Yeah. Yeah, absolutely. But I mean, nobody says that you cannot do something similar with a different algorithm. We just decided to mix 2 random forest classifiers because then it's very easy to control how the complex classifier is set up. But we also discussed at some point, why not mix a KNN with a random forest or a support vector machine with, I don't know, a KNN. I mean, right now I don't have an idea how I would do that mathematically, and we just thought that this is the easiest because I just mix trees from here and there and control the composition of the forest, right? But for sure, other combinations I think should be completely possible. And this idea of transferring knowledge obtained with one algorithm and then feeding in information from another one. But we haven't tried it. Yeah. Again, very recent. Yeah. Yeah.
So, since I'm not from the field, these surface parameters, they are the standard ones
Yep.
that everybody uses.
Yep.
Any of them has something to do with entropy, for example, or this complexity
I mean, there are also surface parameters that are called entropy, so they basically describe the randomness of a surface, if you want. And I think the best one here that goes into direction is actually STR. It describes the isotropy of a surface, or the anisotropy in our case, and that has definitely to do with that. So yeah, I think there are a few that are actually going into this direction. Yeah. And yes, all these parameters we use are defined in the ISO. So it's an ISO norm. I forgot the number I showed you yesterday, I guess, and yeah, even more, but the software we have can very well calculate those in a robust manner, and that's why we typically for our studies stick to a set of 20. That's the typical ones I always show, and then Netcore does whatever it does, and here we end up with that. Yeah. Okay, all right. Okay, so if you could follow me until here, then there's a good chance you can also follow what I'm going to show on Saturday, because will not be then like teaching level, but really what we're working on, like really research, how we try to tweak the system such that we actually can solve a real problem in material science, but it will use the ideas that so far I've shown. Okay, then I think it's time for coffee.